Well, good evening and welcome to Space Oddities. How are you all on this Tuesday evening? We hope you're well. Thank you for joining us as always. I'm joined this evening by Roger and Daz and Lou. I'm afraid Michael is not well, bless him still, but we wish him all our best. He's in the chat if you want to throw some insults at him. So there we are. So this evening on Space Oddities, what have we got for you? Well, tonight we're tackling the subject of time travel, which obviously is prominent in a lot of science fiction literature, and it's a subject that people seem to love talking about. So we thought we'd talk about it this evening. So before we start, viewers, a little question for you: if you could travel through time, when would you travel to and why? So if you've got any thoughts about that, put it in the comments, and we'll have a chat about it. So just before we go any further, we've also got tonight our usual Constellation of the Week from Roger. Daz will be looking at time travel in popular culture. Lou will be giving us the science behind time travel. Is it actually possible? Can we time travel or not? Will it ever be possible? And I will be looking at the wonderful subject of black holes and time travel. So that's what we've got lined up for you this evening. We've got Einstein of the Week. We've got the latest news. And there we are. So let's just do the normal housekeeping stuff. Hope you all had a great week, by the way. Of course, we all time traveled on Sunday, an hour back into the past.
Except you did.
Rather confused.
We're now on different world lines. So I don't even know how I'm talking to you.
It's all a bit Star Trek, isn't it? It's all a bit crap. So yes, so we all did a bit of time traveling at the weekend. So this is rather apt that we're doing it today. So anyway, if you would like to support Space Oddities, one way you can do it is to buy us a coffee, because astronomers' lives matter. You can click the link that just appeared in the chat, or you can scan the QR code that's just popped up on the screen here at the bottom, and that will take you to the Buy Me a Coffee page, where you can keep us going in caffeine. All money donated to Space Oddities in whatever form goes towards keeping the channel running. So we're very grateful for your support, very grateful for your help. If you would like to see us carry on with the science that we're doing and trying to bring you science in a fun, informative way, which is what we strive for, then please do support us by keeping us going, basically. Of course, you can also go straight to the Space Oddities shop, where you can buy your Space Oddities t-shirts, which probably aren't really that necessary now. But we also have wonderful warm Space Oddities hoodies, and they will keep you warm during this cold autumn. So that's that. You can also make a donation directly to Space Oddities by clicking the super chat icon underneath the chat window there, the one with the $sign on, and you can make a donation directly there. All amounts of money are received, no matter how huge. So please keep us going and on the air by supporting us, because like any other channel, we have bills to pay. All of this stuff doesn't come free, I'm afraid. So we've got a big bill coming up at the beginning of November. So do support us if you can. Any amount is gratefully appreciated, and it will help us stay on the air, as it were. Okay, well, what we're going to do, because Lou is, I presume you're teaching this evening, Lou, are you?
Yep, teaching, and it, because you guys have dropped back to whatever you call your time. I'm still on my EDT time.
Right, well, they've dropped back to GMT.
GMT, okay. Yeah. Oh, is that what it's called? Okay.
Yeah, Greenwich Mean Time. Because
heard of that.
Because
no, it stands for Give Me Tea.
Have you ever been to
have you remember we're astronomers. We stay up late. We need that caffeine, guys.
Absolutely, keep the caffeine coming. Have you ever been to Greenwich, Lou?
I have not.
Oh, you'd love it. You'd absolutely love it. And you can stand with 1 foot in the Eastern Hemisphere and 1 foot in the Western Hemisphere over the line. So that's pretty cool. When we were there in the summer, I was desperately trying to get my daughter to do it, and she didn't want to do it. She felt so self-conscious standing there astride the Meridian line with me taking a photo of her. But I got her to do it in the end by just threatening her. So that worked.
I haven't been to Greenwich, but as you know, I just came back from Iceland, and Iceland sits right on two tectonic plates.
Yes, it does.
And they'll give you dry suits, so you can go swimming between the plates. It's pretty cool. I didn't do it.
Wow.
It sounded too cool.
Wow.
Ah.
And it's not a little thing. I mean, it's a chasm right across the country. It's absolutely amazing.
The country's broken.
Yeah,
Yes.
yeah, absolutely. All right. So time travel. Has anybody put anything in the chat yet? And if not, why not?
I think Sandra put something, but I guess all our viewers are coming in and saying hi. So
Right. Okay.
So
the question is, for those of you that have just joined us, if you could travel in time, either into the past or into the future, when would you go and why? So that's the question for this evening. And just think about that and put your answers in the chat, and we can talk about it. So we're going to go straight over to Lou because he's teaching. So Lou, I'm going to put your stuff up on the screen now. So time travel. The question is, can we scientifically? Is there any? Is it a goer, time travel? Is there any reason to think we might be able to time travel? So here we are.
So time travel. What is it? We may even need to define what time is. Is it possible? If it's possible, how would you do it? And what are the risks of time travel? What do you think? Well, look, guys, this is not. I mean, we make a lot about this. Can you time travel? How do you? Look, is time travel possible? Yes, absolutely. We are doing it now. We are always moving through time. We are time travelers. I think that's all I need to say, actually.
Right, thank you, Lou.
So that's my presentation.
Thank you. Yeah, thank you. Very good. Well done.
Short and sweet as always.
Short and sweet. But if we wanted to go a little further, could we visit the past or the future at will? That's the real question. What are the implications of such a journey? Can we change the past or future? These are big questions, right? They rely on our ability to perceive time, right? Which is not straightforward. To remember events, that's the past. To imagine possibilities, that's the future. None of that exists now, right, in the present. And it also relates to our understanding of just what time is. Right? So let's explore that for just a moment. Okay. So what is time? Time might be described as the continuous, and I'm putting question marks by the word continuous. There is some evidence that at the Planck scale, time is not continuous, it's quantized, and that space-time is discrete and quantized. So more on that later, but let's stick with continuous. Might be described as the continuous progression of events from the past to the future, right? Because time moves forward for us in our universe. But it cannot be defined without reference to space, and I challenge you all to do that. It is inseparable from space, as Einstein showed us, and is part of a four-dimensional continuum that we call what? Space-time, right? Space-time.
You know, this is a quiz.
It's a quiz. Yes. I'm grading you all right now. So here's the good news. To understand the basics of time travel, you only need to know two simple things. One is that the speed of light is invariant, meaning it's constant and the same for all observers in a vacuum, in inertial reference frames, in other words, constant velocities. This is a fundamental principle of Einstein's special theory of relativity that he published in 1905, his miraculous year. And it states that the speed of light is a universal constant. This has profound implications on time dilation, length contraction, mass as it forces our concept of space and time to be relative to the observer. Okay. So, well, that's all very interesting, but that's all you have to know. So first thing is, speed of light is a constant for everybody. Everybody measures it the same. The second thing you have to know is the Pythagorean theorem. Oh, and by the way, Pythagoras didn't come up with this. There's pretty clear evidence that the Babylonians knew about the ratios in triangles 2000 BC. But that aside, I think there was something called the Babylonian Plimpton 322 tablet that shows the relationships of different sides of a right triangle. It's about 2000 BC. Okay. You learned this in school. A squared plus b squared equals c squared. And it turns out that this very simple understanding of geometry, understanding of right triangles, gets you a very long way in understanding the fundamentals of time travel. So let's explore that a little bit. We've said that the speed of light is no matter where you go. So here's a problem for you. You are standing on Earth and you see two spacecraft. In this case, the spacecraft are going towards each other, but imagine that they're moving away from each other at 0.7 the speed of light, 70% of the speed of light. One of them's going to your left at 70% the speed of light. The other one's going to your right, 70% the speed of light. Are they going 1.4 C? Have they violated the principle?
No, definitely not.
The answer is no, they have not. You can add those two together if you want on the Earth. But if you're in one spacecraft, because of some math I'm going to show you, some simple-minded math, they don't see the other spacecraft receding from them at greater than the speed of light, in fact, less than the speed of light, and vice versa, because these two spacecraft are in inertial reference frames. They can't really tell who's moving and who's not moving, or who's moving how fast and who's not moving how fast. Okay, so just to get that understanding under our belt. Now I'm going to ask you to imagine a train. By the way, what we're actually doing is we're deriving something called the Lorentz transformations. But just stick with me here. There are two postulates of special relativity, the equivalence of all inertial reference frames that we just talked about, and the consistency of the speed of light in a vacuum that we just talked about. So these principles dictate that space and time are not absolute, but are intertwined together into a single entity called space-time. The transformations mathematically link the coordinates of an event as observed by two different observers, uniformly moving, in other words, at constant velocities. And this replaces the older Galilean transformations at high speed. Under Newton and Galileo, time simply moves forward. Objects move at speeds that can be easily calculated under classical mechanics. No problema. But under Einstein, it's a little bit different. So here we have a train. I have a picture of a train. And there's a person on the train. And that person has a stopwatch with them. And they have a flashlight that's sitting on the floor. And that flashlight is casting a light beam up to a mirror that reflects it back down to the flashlight. All right. So the distance that light travels is twice the length of the height of the train. Okay. Got that? Okay. Now let's go to another situation. You are sitting on the side of the road and you're watching that train go by. and you see that flashlight turn on and shoot its beam up to the mirror. But as you see that, the train is moving forward. It's moving to your right. So the light path does not go straight up. It goes at an angle, even if it's a very slight angle because the speed of light is very fast. But it does go at an angle. And then it comes down at an angle so that the flashlight gets hit by the light some distance to your right from where it was emitted. Okay. So here we are with our two situations. Person on the, by the way, I drew the stick figures here. I took it.
I can tell.
It helped me a little, but it's mostly my work. So we have two individuals observing the same event. The person on the train sees the light go straight up and straight down at the speed of light, because the speed of light is a constant. The person on the side of the tracks sees the light go up at an angle and then down at an angle. And so we now have two right triangles, right? Remember I said a squared plus b squared equals c squared.
Mm-hmm.
This is the law of right triangles. And without going through all the derivation, when we do this, we're able to get something called gamma, which is the constant on the left here, on the lower left, in the Lorentz transformations. That is equal to 1 over the square root of 1 minus the velocity squared, right? That would be the velocity that the train is moving, over c squared. And when you do this, you are able to get time dilation and mass increase and length contraction. Because as you move faster, time will slow down, mass will increase, and length will contract until you go to the speed of light, which is the limiting case. And at the speed of light, if you just look at our gamma here, when v equals c, v squared over c squared is 1, 1 minus 1 is 0. And so you're dividing by 0, so you get infinities. Time goes to 0, mass goes to infinity, and length goes to 0 when moving at the speed of light. And that's all you really have to know. That's how you get time dilation into the future. That's how you travel into the future. And the way that looks, dependent on velocity, is something like this. Here on the x-axis here, on both, the left plot is for time, the right plot is for length. On the x-axis, we have how much that deviates from our normal clock time. And you see that as your speed increases and gets closer and closer to the speed of light, the effect gets quite great. With length is going to contract to 0 at the speed of light. And you can see that effect based on what fraction of light you're going. Okay, so that's kind of interesting, maybe. Now let's look at something else. We have an individual standing on the side of the tracks. We're going to use our train again. And he notices there's a storm a-brewing. And he sees two storm clouds with a lightning bolt that strikes these two trees at the same time. He knows it's at the same time because his watch says so. Okay? Those two lightning bolts struck those trees simultaneously. But in this special relativity train paradox, two observers, one on the side of the tracks we just talked about, and an observer on the train, have different perspectives on whether two lightning strikes are simultaneous. In other words, at the same time. The stationary observer, as we said, on the platform, he sees the light strike each of the trees at the same time. So they believe the strikes are simultaneous. However, an observer on the moving train sees the strike ahead of them first and the strike behind them second, because the train is moving toward the right, toward the front strike, and away from the rear strike. And this is because simultaneity, right, the simultaneity of two events is not absolute in special relativity, and it depends very much on the observer's frame of reference. So you can't say that two things happen at the same time because it's very dependent on the observer. Well, all this is interesting, kind of theoretical, and you might find this in some classroom textbook. But what about reality? GPS satellites rely on our understanding of time travel in order to operate correctly. Both special relativity that we're talking about here and general relativity, which is how time is affected in a gravitational field that Andy's going to talk about a lot more when he talks about black holes. Both of them cause time dilation effects in GPS satellites. And this requires constant correction for the systems to function accurately. Without these relativistic adjustments, errors would accumulate by about 10 kilometers a day, rendering the GPS navigation useless. Okay.
And in fact, this may be an apocryphal story, but the way I read it, when they were testing the initial prototype satellites, if you like, for GPS, they forgot to include relativistic calculations, and they were wondering why the GPS system wouldn't work. And of course, once they realized that they needed to pay attention to Albert, GPS worked perfectly. Once they'd made the adjustments on the atomic clock in the satellite, it worked perfectly.
Outstanding. Right. It can't be ignored. It's real. It's not some fanciful theoretical thing that has no application in our reality. It is real, but we don't notice it usually because we move at relatively slow velocities and relatively consistent velocities. So we have two things happening here. The first is our relativistic effect, a special relativity effect. GPS satellites orbit Earth at speeds of about 14,000 kilometers per hour or 9,000 miles per hour. According to special relativity, which we just looked at, relative motion causes time to slow down for an inertial observer. So from our perspective on Earth, the atomic clocks on a GPS satellite tick slower by about 7 microseconds per day. So time is moving slower, but there's a general relativity effect as well. GPS satellites orbit at an altitude of about 20,000 kilometers, about 12.5 thousand miles. And this is a place where Earth's gravitational field is weaker than on the surface of the Earth, right? So general relativity predicts that clocks in a weaker gravitational field run faster. So that causes the satellite clocks to gain about 45 microseconds per day compared to clocks on the ground. And as you are already surmising, these two opposing effects do not cancel each other out. The general relativity effect, where time speeds up due to a weaker gravitational field, is significantly stronger than the special relativity effect, where time slows down due to high speed. So that's kind of important to know.
Yeah.
This next slide, I think we covered, but let's redress it. Principle of relativity. The laws of physics are the same for all observers in uniform motion. In other words, inertial reference frames, constant velocity, no acceleration. Consistency of the speed of light in a vacuum is the same for all observers, regardless of their speed and regardless of their direction of motion. So we have, in this case, we have two astronauts kind of floating out in space, deep space, right? No reference points. And they're coming toward one another. Each one sees the other approaching. But as they are both in inertial reference frames, they cannot distinguish their velocity from the other. So one is moving and the other is standing still, maybe? Or are they both moving? There is no way to know. Okay? So all inertial reference frames are indistinguishable, and that's an important piece of information for our next slide. As you might imagine, if you really want to talk about time travel, there are a few paradoxes. We're going to talk about two of them today. This is the Bob and Alice paradox, or as most people call it, the twin paradox. So this is kind of fun. This twin paradox is just a thought experiment in special relativity, and it highlights the asymmetry between an Earth-bound twin and a twin who travels on a high-speed spaceship journey. This paradox arises because while the traveling twin, the one in the rocket ship, must return younger due to time dilation, it seems from their perspective that the Earth-bound twin was the one moving and should therefore be younger, right? If you have, again, two spacecraft or an Earth and a spacecraft, and they're moving apart at a constant velocity, wouldn't you expect each one to look at the other and say, oh, wait, your clock's running too slow? Each one should be able to say that. The paradox, in this case, is resolved by recognizing that their situations are not, in fact, symmetrical. So Bob is going to stay on Earth. Alice goes off in the spaceship. From Bob's frame of reference, Bob stays in a single inertial, non-accelerating reference frame throughout the trip. He can apply the standard time dilation formula to Alice's constant velocity segments and conclude that she will be younger upon return. From Alice's point of view, Alice experiences not a single inertial reference frame. She starts in one frame, moving away from Earth. During the turnaround, when she has to turn around and come back, she decelerates and then accelerates into a different inertial reference frame, coming back to Earth. She has an accelerometer, in fact, on board that confirms this. An accelerometer with Bob on the surface of the Earth doesn't register any acceleration, but Jane's does. The change of reference frames during Alice's turnaround that's what makes this twin paradox work. According to the relativity of simultaneity, what is considered now in one reference frame is not now in another, and we saw this with the lightning strike of the two trees. From Alice's perspective, the plane of simultaneity, the set of events she considers to be happening at the same time as her, dramatically shifts during her acceleration. And during this shift, a massive amount of Bob's time suddenly appears to have passed, causing his clock to jump ahead in her calculation. And this jump more than compensates for the time dilation she observed during the constant velocity part of her trip. And so when she gets back, she sees that Bob is an old man and she's still a young girl. Well, that's one paradox. Here's another one. This one's kind of fun. This one doesn't need much explaining, I don't think. You build a time machine. You travel back in time. You meet your grandfather before he procreates, okay? Then you kill him. Then you're not born, so there's no time machine built, but then you build a time machine. So obviously, going back in time is not for the faint of heart. It creates all kinds of interesting problems.
I read a paper a couple of years ago that purported to show that the grandfather paradox would never arise because the universe would never actually let you kill your grandfather when you went back in time. So what it was saying basically, but the scenario, say you're walking down a street, you see your grandfather on the other side of the road, you bring out a gun, aim the gun at your grandfather to shoot him, and at that moment a bus passes in front of you. So the universe will always come up with a way of stopping those paradoxes in time.
I thought you were going to say the universe had gun control.
Yeah.
Maybe not.
The universe police.
Yeah. You're American. What would you know about gun control?
Ouch.
Yeah.
I'm going to flip back a few slides to show you why another reason it's not likely or possible. Remember this quantity gamma, 1 over the square root of 1 minus v squared over c squared?
Yep.
In order to run time backwards, your velocity would have to be negative in this equation. And that's pretty hard to come by, at least by the laws of physics that we understand.
There's just a question popped up about this, Lou, if you would like to take it.
Sure, go ahead.
Oh, I'm on the wrong place. I'm in the wrong place, sorry. Let me just come over here on the wrong machine. It's Deep Burrito, and what he's asking is, here we go. Let me show this. Wouldn't it just split into another time if you killed your grandfather?
Well, that's a matter of theoretical discussion. You could make the case. So here, maybe this might give you some peace. In the twin paradox, where Alice is zooming off and then turning around and coming back, and Bob is staying on Earth, Alice thinks that Bob's time has changed. Bob thinks that Alice's time has changed. So to each of them, the other person is existing in a different reality, or if you will, a different universe, that they have jumped universes. This is a matter of speculation, but that's one way to think of it. So you could make the case for what you're saying, I think. I hope that answered your question.
Yeah, and just as let's go there. As regards gun control, he says just keep both hands on the grip.
Well, we're trying.
Thanks for your donation, Ian. Thanks very much appreciated. The Deep Burrito says we are talking doctor. Yeah, this is the whole problem, Deep Burrito. Once you start talking about timelines and splitting timelines, these things sound plausible in science fiction. But what does a timeline actually mean? And how could one time split into another timeline? So I think it belongs in the realms of Doctor Who rather than actual science. But
Doctor Who and Minkowski diagrams, which we are not going to talk about today, but
no,
we can talk about another time.
That's right. And Barry says, hang on, let's put this up on the screen. Barry says, split universes. Hang on, why doesn't that come on the screen? Yeah, split universes is part of the many worlds concept, which it is, and the idea behind this is that whenever you make a decision, or whenever an event happens, it creates basically another universe, and although there are mathematical reasons for thinking that might be true, to the best of my knowledge, nobody actually takes it that seriously. It's part of the observation problem in quantum physics. So yes, you're right, Barry. Absolutely right. It does exist, but these things are all very difficult. I do remember. This might interest you. I remember I've got a book by David Deutsch. I can't remember what it's called. It's up on the shelf there somewhere, where he goes into, or he puts forward a very good logical argument for why time is quantized, and
not the Planck scale.
Yeah, that's right.
Yeah.
And I remember reading that, and thinking, yeah, how could it be otherwise? But I can't remember what the argument was now. It's years since I read it last. I must get it off the shelf and read it again. But David Deutsch is he Oxford or Cambridge? David Deutsch, I think he's Oxford. He's a physicist, a famous physicist for delving into these sort of questions. So there we are. Right, sorry, Lou, carry on.
Just one more kind of fun problem here. I want to introduce the idea of tachyons. Tachyons are hypothetical. They're theoretical subatomic particles. They fall out of the math, but are essentially impossible to observe. Particles always travel faster than the speed of light. In my when I was doing internship, when I was in high school, I worked at Goddard Space Flight Center one year, and I worked for a guy named Newport, who was actually studying the possibility of tachyons. So we don't know if they're real, but they certainly have some mathematical and theoretical underpinnings. So they always move it faster than the speed of light. And a tachyon experiences time very differently from you and me. Though there's no direct evidence for tachyons, their existence is supported by string theory. So a hypothetical tachyon would have an imaginary proper time, meaning its own sense of time would be radically different and difficult for us to comprehend. It's a bizarre particle. I mean, the bizarre nature of tachyons and their faster than light speed could be used, for example, to send signals backward in time, according to special relativity. Of course, this would create logical paradoxes, such as receiving a message before it was sent, so that's a problem. And from the perspective of an outside observer, a tachyon would arrive at its destination before it was emitted at its source. This effect is why the concept is connected to an idea of a message traveling backward in time. And we have a little game that we could play here to illustrate this. This is kind of fun. Okay, we have two astronauts dueling with tachyon guns. A is on the right. A is on the left. B is on the right. A and B turn back to back and walk away from each other at 0.866 the speed of light with their tachyon pistols. The T prime, in other words, the relativistic time, is 2 times the actual time times the dilation factor, which is gamma. You don't have to think too hard about that. A then counts off 8 seconds and turns and fires at B. Mm-hmm. According to A, B is the one who is moving, right? They see their velocity is essentially standing still. So B's clock is ticking at half speed. Therefore, the tachyon bullet that A has fired hits B in the back after only 4 seconds. But B sees A moving with a slowed clock. So B, wounded, turns around and fires at A, hitting A a full 6 seconds before A fired his pistol. So it's all very weird stuff when you start talking about time travel. Right. But we're all time traveling. When I go out to a conference on the West Coast and jet back, I'm probably a few nanoseconds younger than I would have been if I'd stayed put. It's this kind of thing. And so perhaps you could argue that I've moved into a different universe or different world timeline, or just that time moved a little more slowly for me. That's up to you. I'll end there, Andy.
Right, well, thank you very much, Lou. Thank you very much indeed.
That was very interesting, yeah.
Yeah. So, Lou, I mean, put you on the spot a bit, maybe. So, do you think we will ever be able to travel in time, in the classic science fiction way of getting in a time machine, selecting our date we want to go to, and off we jolly well go?
Well, the first thing is I remember the words of Lord Kelvin in the 1800s, who said, surely there's nothing left to be discovered. All that remains are finer and finer measurements. So when you ask if I think there will ever be, I want to be very careful.
Yeah.
I have heard it said that perhaps humanity's raison d'etre, our reason for being beings that can imagine the universe, is to populate our consciousness and to conquer the speed of light. So,
wow.
Who knows? I mean, the physics that we have to play with today with quantum entangled particles and special and general relativity would not have been possible in the 1800s. It's very hard to say. And I haven't even talked about wormholes, which is more of a space dilation than time dilation. But
well, don't worry, I'll get to that later.
All right. I knew you'd cover for me, Andy.
Yeah.
Sandra says she needs to lie down in a darkened room.
You do that, Sandra. You take your time. This is.
I mean, the theory. I mean, there is the speculation that if you could time travel, you'd only be able to time travel into the past because the past has happened. Yet you couldn't pass into travel into the future because the future hasn't happened.
Yeah,
So,
but Stephen Hawking, was it Hawking or Feynman? Can't remember. One of the two said, "Why is it that we can remember the past but cannot remember the future?" Because what you have to remember is that at the quantum level, there is really no distinction between past, present, and future. And if you look at how Feynman diagrams work, they're actually based on the fact that there is no set direction of time at the quantum level. So there we are. What I would like to do now, before we move on to the news tonight, is to ask the team here if you guys could travel in time in a classical time machine, when would you go to and why?
Oh, man.
who are you going to first?
Let's go to you guys.
I mean, for me personally, I would like to go back to just before the Big Bang so I could watch it and then come back and write some really excellent papers on it and get lots of Nobel Prizes. So,
yeah, that'd be good. That'd be
sort
good.
of thumb your nose at everybody. I know what went on.
What about you,
I mean,
Roger?
that's for me.
What about you,
Who, me?
Roger?
Roger, go, Roger.
Well, I don't know really. I haven't really thought about where I'd like to be.
You'd like to go back to when pirates ruled the sea. Arr.
I'd be like to do see the impact of the meteor that got rid of the dinosaurs.
Okay, yeah.
Oh, right, yeah, fair enough.
Yeah, a little bit more, bit more modern than Daz's viewpoint.
Well,
Yeah.
a bit more morbid, you know, extinction events. Yeah, okay then.
Yeah.
Yeah.
Mine's creative, yours is destruction. Okay.
Yeah.
Mm-hmm.
Lou?
Finally, Lou.
Well, I there's some famous people I'd like to meet. I'd like to meet Newton and just chat with him about his understanding of the nature of reality. I've always appreciated Giordano Bruno, poor
Yes.
guy. So
Yeah.
that would be an honor to meet him. Eratosthenes and the brilliant work that he did, the circumference of the Earth. There's just a whole lot of scientists.
Okay. Well, speaking personally, I mean,
They're
I think
ideas.
it would be good to go back into the past and meet your earlier self and say things like, don't get involved with that girl, or don't have that pint. You'll have a hangover, terrible hangover, all hangovers tomorrow, things like this, bit of advice. But if I had to go back into a particular time, I think I would like to go back to the Victorian era if I had money. And because that was a time of such great technical innovation and societal change, where people were able to have education for the first time. The masses were able to have education for the first time. And there was a general thought that science and technology could change the world for the better for everybody. That sort of optimism. And so many more people were becoming interested in science and technology for the first time. And there we are. I'd love to experience that optimism instead of living in a world where, you know, science is now under attack from all sorts of areas. So I'd like to go back and experience what it must have been like to live in a world that was optimistic about the future, as the Victorians were. That must have been great.
We're talking about that, Andy. I mean, at that time also, what you got to remember, there was a conflict with science, but all science in the church as well.
Yes.
So, yeah, there was this sort of like mismatch. So, yeah, I mean, it would be a very interesting time, like I said, if you can meet the people who are instigating all these discoveries and all these theories. We've got Ian. He said he would like to meet Galileo.
And by
Barry,
all accounts, Ian, Galileo was very keen to meet you too. So there we are.
yeah. Barry said he wished he was a Wild
Wild
West
West
hero.
Nice
And
one,
Derek and Deep Burrito had the same thinking. How about the restaurant
the
at
troll at the end of the universe? Yeah.
And Anne said she would like to meet Carl Sagan, which is
that's a
good
good
call,
one.
that one. Yeah.
Yes, absolutely.
That's very, very, very interesting guy. So
I would love to have sat in on some of Feynman's lectures. I would really love that.
Oh, yes.
Yeah.
Oh, yes.
So there's I don't know if you ever saw it, Lou. He did an interview with the BBC called the Pleasure of Finding Things Out, and it was all about his philosophy about life. And, I've got it somewhere. I'll send you a copy. I think you'd enjoy it. So
He was a crazy guy.
Absolutely
Brilliant, crazy.
Mad bongo player as well. So so yeah. So there we are. Right there, viewers. Well, keep those thoughts coming in. If you could travel, I've noticed nobody said they want to travel into the future. I'd like to do that as well. Just come back in just 100 years and see whether humans have survived the next 100 years.
But you come back well depressed.
Yeah, yeah. But there could be a glorious future ahead of us.
Well, yeah, it'd be the planet would be run by apes.
Yeah, that's true. Yeah, and well, I can see why you'd think that. So, so there we are. Okay, well, we're going to move on now. We're going to go on to the news now as time's getting on. So just give me a second, and we'll move on to have a look at this week's wonderful news.
I'm going to leave you all and wish you good luck. I'll see you next week.
Thank you very much, Lou.
Cheers, Lou. Thank you.
Take care, all.
Take care. All right. Hang on. There we are. Okay. So here's the news for the 28th of October. Just coming up now. Okay. Just let me get to where I need to be for this. Okay. So the news for the Tuesday, 28th of October. Well, the first thing to say is that yet again, Comet Atlas is in the news because don't forget, it's an evolving object that is changing its behavior as it closes with the sun. And the astronomers have captured this dramatic new image of 3i Atlas showing a powerful jet of material erupting from its surface and streaming towards the sun, not away from it. As the comet approaches closer to the sun, intense solar heating is causing sections of its icy surface to sublimate unevenly. Sublimate basically means to turn straight from a solid into a gas without a liquid phase, resulting in a focused jet that stretches thousands of kilometers into space. Now, despite being an interstellar visitor, as we know, the third such object we've ever identified, it's behaving in similar ways to comets within our solar system, reaffirming that the physical processes governing cometary activity can apply even to objects from beyond our solar system. Now, the appearance of this jet pointing in the sunward direction, while the tail obviously still extends away from the sun, highlights how localized bursts of gas and dust can dominate a comet's behavior when heated, because it's closing with the sun and heating up, and obviously the front of the comet is being heated the most, so it's causing this jet of material to erupt, and the force of that material is overcoming the pressure from the solar radiation to push it backwards. So this is why it's firing a jet forward. While we're on the subject of the comet, viewers, just incidentally, we were talking, I think it was last week, about, well, we've talked about it for a few weeks, the amount of nonsense there is about the comet on the internet. Well, that's taken a more sinister turn this week, because there are video deep fakes of famous scientists basically telling the world that the comet is an interstellar spaceship. And we we must apologize. We had a go at the renowned physicist Michio Kaku last week for talking nonsense about the comet. Well, it turns out the videos of him talking nonsense about the comet being aliens and all the rest of the malarkey, they're deep fakes. And he's actually had to come out today and issue a disclaimer saying these videos are fakes. I am not saying these things about the comet. Last night, I found one on YouTube of the extremely famous physicist Kip Thorne saying similar things, saying that the comet was probably an alien spaceship. And again, I gave some of the video to an AI, and it did forensics on the video, and it came to the conclusion that it was artificial, that it definitely wasn't Kip Thorne in reality. But the problem with that video was it was so detailed in technical information about the comet, and it sounded plausible that anybody who didn't know might readily believe that Kip Thorne was supporting this ridiculous idea that it's a spaceship. Because these are being so very well done, these deep fakes, that as I said, unless you wouldn't be able to tell them from the real thing. This is not some flat earther moron on YouTube doing these deep fakes. These are very well thought out, very professional, and it just makes you wonder who's doing this and what's their motivation for doing it and what do they hope to achieve. So anyway, all I want to say about that is be wary of videos of scientists saying that the comet is a spaceship, because they're probably fakes. So there you are. Just thought I'd bring that up while I thought of it. It's all a bit scary, really, if you ask me. Anyway, moving on. Now, you may remember Chang'e 6. Chang'e 6 was a Chinese lunar lander that landed on the far side of the moon, and it returned samples of the lunar soil, the regolith, to the Earth. Now, what they found in these samples are fragments of a rare meteorite type called CI chondrites. These are rocks that are rich in water. Yes, you can have rocks rich in water on the moon, and also carbon-bearing volatiles. And these chondrites are extremely fragile and react very quickly with oxygen or water. They're scarcely preserved on the Earth. However, the dry lunar surface offers an ideal archive for this sort of material. Now, their presence on the moon suggests that outer solar system material rich in water and other volatiles has been delivered into the Earth-Moon system more often than previously thought. That in turn implies that a significant portion of Earth's water may have originated via meteorite or asteroid impacts during the early solar system, rather than from solely internal sources or icy comets. So one idea says that the Earth was born with its water, it was always there. Another idea says that it was comets who delivered most of Earth's water. But now, because of this, by analyzing the chemistry of these samples, scientists hope to refine models of how water was delivered to Earth and the moon, and better understand the contribution of volatile rich material to planetary development in our solar system. So this is another step forward towards solving the riddle of where did Earth's water come from. So little by little, we're getting to answer that question. Now, astronomers using the TESS mission have discovered 3 Earth-sized exoplanets orbiting the compact binary star system TOI 2267, which is roughly 190 light years away. The system is unique of those we've found so far. 2 of the planets transit one of the stars, while the third transits the other star, making it the first known case of a binary system with transiting planets around both stars. These planets orbit in a dynamically challenging environment, giving the stars close orbit, which suggests planet formation and stability can succeed even under strenuous conditions. The twin star backdrop means that if one of these planets were observed from the surface, it could experience double sunsets. Obviously, this is like the picture of the planet Tatooine in Star Wars. Now, this finding challenges previous assumptions that binary star systems are too hostile for rocky planets, and offers a fascinating laboratory for studying planet formation under binary dynamics, when you have the binary systems and stars that orbit them. And future follow-up, for example, with the James Webb Space Telescope, might reveal their masses, densities, and atmospheres. So it is possible for these weird planetary orbits to exist in multiple star systems. So this is a unique system that's been found where the planets do just that, with two of them orbiting one star and the third planet orbiting the other star, which is certainly bizarre. Okay, bit of an anniversary today. On this day in 1971, the United Kingdom launched its first and only satellite using its own rocket system. The satellite, as you may know, was called Prospero. It was also called X3 for some reason. It lifted off aboard the Black Arrow rocket from the Woomera Range complex in Australia. The purpose of the mission was to evaluate communications, satellite components, and a micrometeoroid detector, testing how the space environment affects such systems. Shortly after deployment, the rocket's final stage struck Prospero and damaged one of its antennas, but it did remain operational until 1973. This milestone is significant as it marks the UK's autonomous entry into satellite launch capability, distinguishing Prospero from earlier British satellites carried into space by foreign rockets. So this was a totally British launch system and satellite, and that was on this day in 1971. So there you are. Okay, just to look at some recent gravitational wave events. These are the latest gravitational wave event candidates that I've been able to find. Just quickly go through these. Just let me explain what you're seeing on the screen in front of you. So there's the event ID on the left, the date of the detection, the detectors, H for Hanford in Washington State, L for Livingston in Louisiana, and V for Virgo in Italy. These are the three of the four operational gravitational wave detectors, the fourth being Kagura in Japan. Then the column called P Astro is a decimal representing a probability of the certainty of the detection. So obviously 1 is total certainty. So just to go down these quickly, they're all binary black holes. These are all black hole mergers. So the first one, we've got two black holes of 11 and 22 solar masses. And, you know, none of these have been confirmed yet. These are all hot off the press, so they've yet to be confirmed. So these two black holes of 11 and 22 solar masses merged. Then we've got two of 11 and between 11 and 22, same sort of mass range. Then we've got another one where estimated 22 solar masses and 44 solar masses merged. It's quite more massive there. The fourth one, two black holes of 5.5 and 11 solar masses merged, so a bit of a mass difference there. And again, the last one within the 22 to 44 solar mass range. And as I said, all this data is provisional at the moment. They've yet to be confirmed, but those are the latest candidates for the detection of black hole mergers. More of those next week, I'm sure. Going to move on now to some black hole news. Now, this is interesting. Scientists have detected, as we were talking about it, gravitational wave signals from two newborn black holes, each the product of a merger between earlier black holes. Now, one of these events, the gravitational wave event GW for gravitational wave event 241011, stemmed from a collision about 700 million light years away involving a 17 solar mass black hole and a 7 solar mass black hole. The larger one of 17 solar masses was found to be spinning extremely rapidly, one of the fastest spinning black holes ever seen. The second event, GW 241110, occurred around 2.4 billion light years away, hence 2.4 billion years ago, because as we know, gravitational waves travel at the speed of light, and involve black holes of roughly 16 and 8 solar masses. Now, what distinguishes this one is that the larger black hole of 16 solar masses was spinning in the opposite direction to the direction of the orbital motion. This has never been seen before. It's a first, Why this should be, we don't know at the moment, but these findings do hint at sort of second generation black holes formed from previous mergers and support the notion of hierarchical growth in dense stellar environments. The idea behind this is that you start off with 2 solar mass black holes, let's say, anything really under about 100 solar masses. These merge and form what's called an intermediate mass black hole. And then they merge with another black hole to form an even larger black hole. So there's a sort of a hierarchy of black hole masses. We've talked about this before, and I'm sure we'll talk about it again. But needless to say, these were 2 quite interesting recent discoveries by gravitational waves. And we've got another interesting story here, because scientists have, for the first, measured the kick imparted to a newly formed black hole as it recoiled from the site of its birth merger. Using previously detected gravitational waves from the event GW 190412, they determined the remnant black hole, this is the black hole that was formed when 2 black holes merged, was, as has often been thought, kicked away by the product of this merger at about 112,000 miles an hour. And this means that the star cluster that it was born in, it was moving fast enough to escape that star cluster. The kick results from an asymmetric emission of gravitational waves when 2 black holes of unequal mass collide, and this does produce a thrust, a kick, if you like. Now, if you analyze subtle variances in the wave signal, the team was actually able to reconstruct both the speed and direction of the recoil in 3 dimensions. This is a breakthrough, and it offers a new way to probe black hole physics and environments, opening the possibility of linking gravitational wave signals with traditional electromagnetic observations of the newborn black hole's journey through space. So we're now able to map the direction of travel and the speed of the black hole, which, as we said, results from when you get 2 black holes of unequal mass, and the gravitational waves impart a sort of a kick to the newly born black hole. So that's a big step forward in gravitational wave physics. There's another interesting story here that researchers propose a trio of space observatories, the James Webb Telescope, Euclid, and the Nancy Grace Roman Space Telescope, which has yet to launch, as we know, could work in tandem to uncover the universe's earliest supermassive black holes, or SMBHs. Now, the problem is that, as we know, the James Webb's already seen supermassive black holes when the universe was under 1 billion years old, but standard growth models say it should take much longer for these black holes to form such enormous masses. Now, to resolve the discrepancy, astronomers are exploring heavy seed, so-called heavy seed pathways. This is when a giant cloud of molecular hydrogen spontaneously collapses under its own gravity directly into a black hole. And these typically form much bigger black holes than sort of stellar mass black holes. They form massive black holes. So this could be how we get supermassive black holes so big in the early universe. And this could theoretically just happen just a few 100 million years after the Big Bang. So these supermassive black holes might exist at redshifts of 15 or more. And what that equates to is about 250 million years after the Big Bang. Now, the James Webb is great. Sorry about that. The James Webb is great for this because it's got high resolution infrared view, and it's ideal for a detailed follow-up, but it has a very small field of view. Now, by contrast, the Euclid and Roman telescopes offer much wider survey capabilities, and this enables them to scan large patches of the sky and identify candidates which the JWST can then scrutinize spectroscopically. So simulations suggest that this combined strategy might detect on the order of 100 supermassive black holes forming within just 250 million years after the Big Bang, placing strong constraints on formation models and giving us more information about how these supermassive black holes did manage to form so early in the universe's history. And then lastly, astronomers have discovered the first confirmed group of luminous dust-shrouded quasars powered by supermassive black holes in the early universe during cosmic dawn, that period of the universe where the maximum amount of star formation and gas production was happening. Using wide field surveys combined with deep infrared follow-ups, they found 7 quasars embedded in thick dust clouds that absorbed nearly all their ultraviolet emissions and a large fraction of visible light. The brightness and inferred black hole masses are comparable to previously known unobscured quasars of that epoch, yet their dust concealment means they've only just been discovered. They've been invisible until now. But the team estimates that the actual number of quasars at this early time may be about double previous estimates once the obscured population is accounted for. This finding emphasizes that many early cosmic black hole growth phases could have proceeded behind veils of dust, altering our understanding of early galaxy and black hole co-evolution. This idea that black holes co-evolve with the galaxy, and it's a bit of a chicken and egg situation, because the question has always been, does the galaxy develop first and then the black hole in the middle, or does the black hole develop and then the galaxy forms around it? So hopefully this will shed some light on that as well. So there you are. So that's the news for tonight. Hope you enjoyed that. Any questions, please obviously put them in the chat. So there we are. So a lot going on with black holes at the moment, that's for sure. So there we are.
I was talking about last week with the little red dots.
Yes, that's right. That's right. Yes, if you remember, we went into little red dots in quite some detail a few weeks ago.
And of course, they were saying there that the red dots could be black holes shrouded in the clouds, like you're talking about.
That's right.
Of course, that means they're glowing very brightly, but then, of course, because they're shrouded in the dust, they look like a star.
Yeah.
So, it's very, very interesting. We need to get these things, looking at these things.
Could you excuse me for one moment?
Shelley says, what does Shelley say? She said, damn dots. Yeah, them pesky dots.
Sorry, I've got a cat screaming at there to come in.
Okay, priorities.
Yes, so we have some questions.
Yeah, well, I think Shelley had a few.
Yeah, Shelley says, what if 3 black holes started spinning in redirectional way? Could you rephrase that, Shelley? I'm not quite sure what you mean by that.
I think Shelley's talking about if they start spinning in different directions. That's basically what she was asking. Because you had that one where the 2 spins were in opposite directions. I think that's what Shelley's on about.
Well, we don't. We've only got so far an observation that seems to show 3 black holes involved in a merger. That must be quite rare. But I don't think there's much information about that at the moment. So we're just going to have to say pass to that at the moment, Shelley. We don't know. And yeah. Any others there, or is that it?
I think that's it. I think Shelley was. I'm just scrolling back a bit. See what I see.
Yeah, I think that was it.
Sorry.
Yes. Yeah. So yes, there's a question there from Shelley. May I ask if the Gemini Observatory tracks all asteroids? No, it doesn't. It's only really interested, I think, in NEO's near-Earth objects, potentially hazardous asteroids. I don't think it tracks all of them.
Yeah,
I may be wrong about that.
Many observatories monitoring the.
Yeah, I mean there are lots of observatories monitoring asteroids all the time, but I think is it the Gemini South Observatory? Is it North or South? I can never remember, or both of them. I think they are specifically looking for hazardous asteroids. So I hope that answers your question. Okay, right. Well, there we are. So what we're going to do now, just remember the questions, viewers. If you could travel forward or backward in time, when would you go to and why? So if you haven't answered that and you want to answer that, put that in the chat. So there we are. Kenneth says strong aurora tonight. Oh, lucky you. Ken.
Mm.
I want to see Aurora. So
Turned all my alerts off because I don't want them pinging while I'm here.
yeah, absolutely. So
Mm.
so there we are. So what we're going to do now, we're going to carry on with this business of time travel. Daz is going to have a look at time travel in popular culture. So let's listen to Daz and take it away, Daz.
Right, just let me get to the right place on. Right, there we go. You can see that, can you? We all know who that is.
No idea. No idea.
No. It's from that famous documentary, Terminator.
Is that a Cyberman on the left?
No, it's not a Cyberman. It's a T100, is it? T100 or something like that. It's basically it's Arnie with his exoskeleton. That's his exoskeleton, and then on the right you've got Arnie with his actually flesh and real flesh, which is fed by blood and all that. That's how he was able to travel through time.
Okay, can I just ask a question about that? Why is he tall? Why is he taller than his exoskeleton?
He's not. You can see he sat on a bike. Look, you can see the handle of the bike.
So. Oh right, okay, all right.
Yeah, okay. That's Andy, you thought you got me there, you didn't. Anyway,
how do you know the exoskeleton isn't wearing high heels?
Well, because I've seen it. It's not wearing a dress. Anyway, let's get on with this because, like I said, now this I could have, basically to do a presentation justice, you have to really. It would take you a week or so because there is so much. Now, one thing I did say, and I wish people would tell me off for it, is that I tend to waggle my cursor around. As you can see, I've been doing it just recently, and I didn't run until I watched the playback that I realised how annoying it is. So I'm trying to pull it out. I'm going to use the different controls this time. Okay. I'll only use the cursor if I just want to point something out. So anyway, as I said, we're going to be talking about time travel in popular culture. We're looking at film, we're looking at television, and we're looking at literature. So it's going to be a quick resume. And I said there was so much out there, and there's lots of things that I can remember that it's not even included in what I'm going to talk about tonight. So basically, again, and what I've done is I've put some slides up, and like this one, I mean, we all know what this is. This is Terminator, and this is a spurned a big franchise of all different Terminator films. And this is what a lot of these things have done, and we'll pop through, and you can tell me which ones are. I haven't labelled some of the slides, so I want you to. I mean, most of them you'll get. I mean, there people are talking about it now. It says Sandra said she loves the Terminator movies. Derek's talking about Skynet, and of course, if you remember I think it was Terminator 2, where they go to kill the scientists who had from part of Skynet. It worked at Cyberdyne. What was it called? Cyberdyne something.
Yeah.
But his name was, guess what? James Dyson. And of course, so he started with vacuum cleaners, and then he went on to build the Terminator. So anyway,
makes sense.
Watch what Mr. Dyson's doing in the background. Right. So anyway, so here we are. This is, as I said, this is it. So what we're looking at is the time travel in popular culture. An exploration of how literally film and television have captured our imagination through temporal journeys, both physical and mental. And again, this is where, because there's two types of time travel in the stories. One is where it's done with machinery, and there's also temporal, which is basically when, say somebody's in a coma or something like that. I don't know if people watched A Life on Mars on television. That was where a bloke was in a coma, and he went back to I think it was the 60s, early 70s. He was a policeman, and he ends up a policeman there. And of course, he has to deal with sort of like the Sweeney type attitude of beat confessions out of people while he's all politically correct and things like that. So that was what we're going to be looking at. So here we are. We're looking about time travel. So what we're going to be looking at, I've just told you really. Literary foundations, where it all began, pioneering novels and stories. cinema's temporal adventures, Hollywood's love affair with time travel, and television time loops, episodic explorations of temporal paradoxes. Mind versus machine, physical journeys versus conscious transfers, cultural impact, and why we're obsessed with rewriting time. Of course, Ian's just mentioned Doctor Who, of course. Yeah. So again, we all know what this car is from. It's the DeLorean. And if you want to guess, I won't tell you until the end of this slide what the actual thing was. I mean, I think everybody will get them. I mean, it does come up several times tonight. So there are two types of temporal travel. Time travel narratives generally fall into two fascinating characteristics: physical displacement through machinery or phenomena, or that's time rifts, and conscious transfer, where minds journey whilst bodies remain anchored in the present time. Literally pioneers. Oh, messed this slide up, didn't I? Time travel as a literally device emerged in the 19th century, establishing tropes and paradoxes that continue to influence modern storytelling. Well, I'd actually counter that with saying that the earliest story that I found was from 1733, and it was called The Memoirs of the 20th Century, and it's by a chap called Samuel Madden. And it was basically a story of a guardian angel traveling back in time to 1728, carrying letters from 1997 to 1998. So I would counteract that 19th century. So we've got, of course, we've got things like Christmas Carol, where he travels through time, answer in the present, just basically teach him what his actions in this time will have repercussions like in the past and also in the future. So Mark Twain's a Connecticut Yankee in the court of King Arthur's court. Of course, that's a modern man goes back to medieval times. H.G. Wells, and we'll be talking a little bit more about that. The Time Machine. Now, the Time Machine. I'll just say that for later. Gregory Benford's Timescape explores consciousness-based temporal communication. So here we are. Here's the Time Machine. Now we all remember this. Right? Can anyone tell me in the chat when he travelled forward in time? What were the two races that he actually met? What were the names of the two races that he actually met? We will answers in the chat if you got time. So anyway, so here we go. H.G. Wells, The Blueprint. Now the actual precursor to the Time Machine is a book that Herbert George Wells published in 1888, and it was actually called The Chronic Argonauts, which sounds something worse than hemorrhoids. So that was the precursor, and I think it was the blueprint for the actual story called The Time Machine, which was actually published in 1895. It established a fundamental concept of a mechanical device enabling temporal displacement. Wells introduced the idea of time as a fourth dimension, navigable through scientific means rather than magic or divine intervention. And I'm waggling my cursor about, tell me off.
Yeah.
His vision of traveling to 802,701 AD and encountering, who was it? The Eloi and the Morlocks. Created the template for dystopian future exploration that countless works would later emanate. So literally mind travel. Now I only knew of one of these. So we've got the Slaughterhouse 5 in 1969. And this is about conscious displacement. Rather than physically journeying through time, some protagonists experience temporal shifts through mental projection or memory access. Kurt Vonnegut's Slaughterhouse 5 in 1969 features Billy Pilgrim becoming unstuck in time, experiencing moments from his life non-linearly. And then, of course, we've got The Time Traveler's Wife. I think most of us have seen this. And this is Temporal Perception. Audrey Niffenegger's The Time Traveler's Wife, 2003, presents involuntary chrono displacement as a genetic problem. Henry detaches from the present without control, creating a meditation on love across temporal boundaries.
It's a good book, actually. Really good book.
Yeah. There we go. China. Cinema's golden era of time travel. Film brought time travel to vivid life through special effects and visual storytelling, making the impossible feeling tangible. In the 1960s, 70s, of course, we had The Planet of Apes, which is an ongoing franchise. They're still making those films. And time after time, 1979, explored the dystopian futures and paradoxical pursuits. 1980s, The Terminator, I'll be back, and the Back to the Future, of course, we've seen those already, defined mainstream time travel. And 1990s to 2000s, complex narratives emerged. The 12 Monkeys, I don't know if anyone's seen that. That's quite a good film.
Yeah.
That's where Bruce Willis, actually, he doesn't save the planet in that one. Primer and The Butterfly Effect, and that's quite a mind-bending film as well. The Butterfly Effect in 2004. So there we go. And we're back to the DeLorean, and of course, to get back, they had to strike the clock tower at a specific time. So Back to the Future. Robert Zemeckis, 1985 masterpiece, made time travel accessible and fun. The DeLorean-based time machine required 1.21 gigawatts, and traveling at 88 miles per hour became an instant cultural icon. The trilogy expertly balanced paradox prevention, the butterfly effect, and the ethics of altering the past, all wrapped in comedy and adventure. Now, everybody must know that one on the left. So, physical time travel in films. Mechanical devices, from DeLoreans to phone booths, cinema loves visible time machines that ground the fantasy in pseudo science. And of course, that there is from the Time Tunnel, which was a 70s TV
60s.
program. Sorry?
60s.
60s. Was it that early? I thought it was the 70s. Oh, my bad.
60s.
Must do more research. Bad boy. Of course, the middle is, anyone got a clue? Oh, God, it's written there. Interstellar.
Would that be Interstellar by any chance?
Oh, well done, Andy.
Thank you.
2014 used wormholes and relativity. And Superman did in 1978 reverse the Earth's rotation. Of course, it was to basically rewind time so that he could save his bimbo friend.
Yeah, like that could happen.
Yeah.
Yeah.
We haven't tried it yet. And then, of course, you got the sort of like the adventure films like The Avengers Endgame 2014, popularized quantum realm travel as a method to revisit the past. That's where they go through portholes and things like that. So, right. Cinema mind travel. Films exploring conscious-based time travel often delve into memory, dreams, and psychological displacement rather than physical machinery. Memory manipulation, Eternal Sunshine of the Spotless Mind, 2004, navigates memories during their erasure. That's all right, wipe somebody's mind. Dream states, Inception, 2010, layers time perception within dreams, where minutes become hours. Conscious loops, the source code transfers consciousness repeatedly into another's final 8 minutes. All right, so here's some of the more favorite ones, more of the TV ones. Television's temporal playground. The episodic nature of television allows for extended exploration of time, travel concepts, and building complex mythologies across seasons. And of course, Doctor Who. Now, nobody, I don't think anybody could say that they don't know who Doctor Who is. So Doctor Who since 1963, and I can remember sitting behind the chair watching this, absolutely terrified, but I still had to watch it. The Time Lord has explored time and space in the TARDIS, establishing the longest running time travel narrative. Star Trek, there's another documentary. Multiple series have featured temporal anomalies from the Next Generation's Yesterday's Enterprise to countless others. The loop episodes from The X-Files to Supernatural and the Groundhog Day. I think Ian mentioned the Groundhog Day earlier. Format became a television staple. So Groundhog Day is where you keep reliving the same point in time. Modern paradoxes, The Dark, which is 2017 to 2020, and the Umbrella Academy, that's what this picture is, weave intricate multiple generational time loops. So basically, basically your imagination is your limit. You can actually do virtually everything within television when you're doing this. So anyway, Doctor Who, the TARDIS effect. Doctor Who transformed time travel into a vehicle for exploring human history, alien worlds, and moral dilemmas. The show's flexibility, regenerating its lead actor and visiting any time period, has kept it fresh for 6 decades. Oh, I lost interest years ago. The TARDIS, now it's time and relative dimension in space, disguised as a 1960s police box, became one of television's most recognizable icons, proving that time machines needn't be sleek to be beloved. Just a quick pop quiz. Which other more up to date? Well, I'll say up to date. They're not really now. Which other film franchise used a telephone box or 2 young men to travel round in time? Can you remember what films they were? They'll be coming up soon. So here we are. We've got TV Minds Travel Narratives. You got Quantum Leap. I can remember watching that, and I think you still watch it on the TV. Sam Beckett's consciousness leaps into other bodies throughout recent history, correcting mistakes while searching for his way home. And then you got Russian Doll, 2019, 2022. Nadia repeatedly dies and reawakens at her birthday party, trapped in a temporal loop. She must decode and escape. And then we got Devs. Quantum computer enables viewing any moment in time, blurring determinism and free through observation rather than travel. I think that's a German one. We got Tenet. I think we mentioned that earlier on.
Mm-hmm.
The grandfather paradox. The classic dilemma. If you travel, which is what Lou was talking about, if you travel back in and prevent your grandfather from meeting your grandmother, you're never born. But then who travelled back? This logical impossibility haunts time travel narratives. So we've got narrative solutions. Stories resolve this through fixed timelines. You were always meant to go back. Multiple universes creating alternate realities, or self-consistency. The universe prevents paradoxes, which is what Andy was talking about. With things like Looper from 2012 and Tenet in 2020, explores these mechanics extensively. Of course, this is another franchise, and I think no one needs introduction to this. And of course, it's the Planet of the Apes franchise. And again, this one is still ongoing. It's still being made now. They're making fresh films of this. And to be quite honest, in a way, it's almost kept some of its freshness, actually, with new storylines and things like that. So, of course, we had Charlton Heston was the first chap who travelled through time. So why we're obsessed with time travel. Correcting regrets. Time travel offers the ultimate second chance, the ability to undo mistakes. save lost loved ones, or change pivotal moments in our lives. Historic tourism, experiencing history firsthand, appeals to our curiosity. We long to witness dinosaurs. Yeah, that'd be nice. Meet Shakespeare, not so much, or he talks funny, and or watch historical events unfold. I think most people go along those lines. Glimpsing tomorrow, humanity's perennial desire to know the future, whether utopian or apocalyptic, drives our fascination with forward time travel. Exploring identity, meeting our past or future selves poses profound questions. Who would we have become with different choices? Again, this is sort of like branches in your timeline. Are we the sum of our experiences? Fixed timelines via the multiverse. On the left, this is the 12 monkeys that I was talking about earlier. Fixed timeline. The past cannot be changed. Attempts to alter history were always part of it. 12 Monkeys and Harry Potter and the Prisoner of Azkaban embrace this deterministic view where time travelers fulfill predetermined roles. And branching realities, this is Rick and Morty, which is a television series. Each change creates an alternate universe. The Avengers Endgame, and as I said, Rick and Morty use this model, allowing consequence-free alterations, at least for the original timeline. Now, this is again, we're back to Doctor Who, and this is one of the original. This is Doctor Who and the Daleks, which is back in the 60s. Cultural impact. Time travel has transcended entertainment to influence language, philosophy, and scientific discourse. 60 plus years, so it's 60 plus years of Doctor Who, the longest running sci-fi series celebrating temporal adventures. 1.9 billion endgame box office. Time heist narrative captivated global audiences, and 100 plus time loop episodes across television. The Groundhog Day format remains endlessly repeatable. Here's Bill and Ted, and this is the answer to the question I asked: which other franchise used a telephone box as a time machine? And of course, it was Bill and Ted, which again, I think there was a trilogy of films on this one. Modern masterpieces. You've got The Dark, again, the German series, which I must admit I haven't heard of. Weaving four interconnected families across multiple time periods in a closed loop of cause and effect. Tenet, which we were talking about earlier. Christopher Nolan's exploration of inverted entropy, where objects and people move backwards through time. And About Time, 2013, Richard Curtis, gentle meditation on using time travel, not for grand gesture, but for appreciating life's small moments. So the enduring appeal. Time travel stories tap into our deepest desires to right wrongs, recapture lost moments, and explore the fundamental question of whether our choices truly matter or if destiny is immutable. Whether through gleaming machines or the power of consciousness, time travel narratives continue to evolve, reflecting our changing anxieties and hopes, whilst asking timeless questions about free will, responsibility, and the nature of causality itself. The end. Hope you enjoyed that.
Thank you very much. Wonderful. So, if you just get rid of that off the screen, Daz.
I'm just doing it. There we go. It should be dead going now. There we go.
Ooh.
Thank you very much. So, yeah, I mean, there's a lot of time travel in popular culture, and that, of course, reflects that people do want to travel in time, even though we don't know of a way of doing it technologically. But just a little later on, I'm going to be talking about one time machine in the universe that definitely does exist. But we will come back to that, because now we're going to go over to Roger for this week's Night Sky Guide. I'll just say that again, and the gallery. So take it away, Roger.
Okay, so here we go for the end of October into November. Oh, there we go. So we're currently experiencing a first quarter right through to getting through to another full moon. So the skies will be getting a lot of moon glow in the night sky. But as you can see here, through the looking south, we've we've still got some of the constellations that we've been experiencing through the summer, but now they are now disappearing with the winter constellations coming up through. Saturn is still looking quite reasonably high in the sky for us, but not too bad. And as we can look forward over to the southeast, we've got Orion coming up through. And that is all good news for us. And we've also got Jupiter coming up through quite nicely as well.
Fantastic. About time too.
Absolutely. So through the morning, we've got Jupiter rising up through Gemini, but we've also got shortly before dawn, Venus coming up through as well. So all's looking well. All nice to see that we've got there. So we've got, when we do get the full moon, it's going to be a hunter's moon.
Of course.
Yes. And
Yeah,
it'll be another one of those slightly larger ones, which we like to call the super moon.
Yeah, we call them poachers.
Wash your mouth. Wash your mouth.
Yeah, okay. And we've still got a wee bit of the Orionids coming through, which is the debris from Halley's Comet.
That's all one.
And well, you have to have a clear sky to see that.
Yeah,
and then we've got we've got the Jupiter and Saturn still nicely up in the sky for us to be able to get that. So we've got the Hunter's Moon, which we've got almost at the end of the month, which is, well, according to that, it's tonight, but it's not a full moon yet. How did that happen? So we've got the blood moon phenomenon. I don't know.
Well,
Somebody's got a bit confused.com here.
yeah.
So atmospheric scattering, which is why the moon always looks more of a dusky red color. It's just the atmospheric dust that we're looking through to get all that. So depending on how badly polluted the sky is, gives you the more dramatic effect. I mean, as in Canada that we had earlier on in the year, we've got some rather spectacular blood red type moon rises. So that can be quite interesting. So, when we've got the full moon coming out through when you had it for the autumn equinox, it was about the closest it was. So the 100th moon is historically used for through various cultures. They used it for hunting ready for the winter, using the moonlight to help with the darkening skies to be able to go out hunting at night. And it's blue light scatters through the Earth's atmosphere while red wavelengths penetrate, creating the iconic red-orange tinge. There we are.
Yeah, as we call that poaching.
Yeah. So we've still got some of the Orionids up to 10 to 20 per hour. So keep an eye out for that, although it has recently gone over its peak. But obviously you do get quite a lot of stragglers, so it will become quite interesting to find one. And we usually see them after midnight, preferably after moonless conditions, but that's becoming a bit more of a challenge. So we'll probably not see quite so much as we get through the week, unfortunately. So we've got Jupiter and Saturn still up in the night sky, quite at a good location. So Jupiter will be becoming much better as it's in Gemini. So we've still got quite a few months of that, and it will become a a better, more visible, stable object to look at through the hazy, wobbly atmospheres that we do usually get. And Saturn is still quite good, even though we've still got the very narrow angle of the rings, unfortunately. So they are widening. So all is not lost. So we've got the Hunter's Moon rising near Saturn, and on a few days later we'll be coming up near Jupiter. So all's well and good there, if you like that sort of thing. So we've also got in the northern sky we've got Cassiopeia, and we've got Pegasus, which we have got quite high up in the southern skies, so it's starting to still be quite interesting to look at. And we've got Orion coming up through in the east, and we've got the Milky Way, which the core is pretty much gone down now, so you will get glimpses of the tail end of it as it's getting darker now, but for very little time, unfortunately. So we've got all the similar information there. It's a bit of a repeat. But we've got the Leonids coming up through, and this is from Comet Tempel-Tuttle. So that might be worth a look at if you're into the meteor watch. So that could be quite interesting. And we've also got the winter constellations coming up through more easily now that we've got the clocks back. We have got some entries again. Thank you all once again for our gallery. And our first entry is from Kevin Earp of Comet Lemon.
Oh, Kevin's on the lemon.
Yeah, a lemon. And this one was on the 21st, so this was exactly a week ago. Here we go.
Whoa.
That's a lemon entry in the gallery.
Yeah.
Mm-hmm. Yeah.
I think
And,
is that our first lemon in the gallery? I think it is.
It is.
It's
It is for tonight. Yes.
It's beautiful. Kev.
And
What a lovely image.
You get very, very interesting day-to-day images, and you can see even over the hours how dramatic the tail changes its shape. It's you know, it's amazing. So all well and good with that.
Well done, Kev.
Yeah, well
Well done, Kev. And then he goes on to photograph the moon, and this is Petavius on the Eastern Terminator with his Celestron Edge 8-inch.
Oh, nice.
Nice.
Lovely
Yeah,
one of potatoes.
Yeah, and you can see the collapsed lava tube there in the crater there.
Yeah.
It gives you a very good outline of how the shape of that crater is.
Fantastic. Well done.
Very, very nice. And we've got our first submission from Anne Sanderson.
Oh, thank you, Anne.
Yeah. And this is using her C-Star S30 on the Sol Nebula. So this is 101-minute exposures, and this is her result.
Wow.
Yeah, you can start to see the outline of that. Very nice.
Yeah, definitely. Well done, Anne.
Welcome
Don't forget, Anne, that this means that you now have your own gallery on the Space Oddities website, which is https spaceoddities.space, because everybody who submits images gets their own gallery on our website. So if you can go and have a look at that and amaze and impress your friends and family. So there you are.
Yeah. Yeah, they are. Yes, they are all on the gallery as of today.
That is gorgeous.
From tonight. So Jerry has managed to capture a flying dragon nebula in Cygnus with his 4-inch Esprit telescope.
Wow.
And you can see why it's called that, can't you?
Yeah, look at the detail.
It's sort of flying towards you with the tail trailing behind.
Yeah, definitely. Beautiful. Absolutely beautiful.
Yeah.
Well done.
It is.
Something that I've not captured yet. Perhaps I better.
Well done, Jerry.
And we've got one from Michael. One from Michael, which was done in Australia.
Oh.
So this will be upside down.
Yeah.
Lovely, Michael. Michael goes south.
Yeah. Yeah. So he's got quite a few
Beautiful.
nice
Well done, mate.
spots there. Well done. And there we go. So, and here's my entry. I put it at the end because I didn't want to put mine next to Kevin's, because mine doesn't shine as well as Kevin's, because mine's was done as a more wide shot, because I couldn't take it from the garden because the trees were in the way. So I had to go and move my little DSLR out into a field to get this picture. But you get an idea of the length and shape of the tail coming out from the back of the from the telescope there. So yeah.
Yeah,
So
very nice, Rod.
Not as detailed or as that, because I didn't.
No, but it's a nice composition. It's because you've also got is that a satellite on the right hand side in the middle?
Well, I think it might be a satellite, but it could also be a meteor or something.
Yeah, it could be.
I think it might be. Yeah. Anyway,
Nice.
so that's what we have for tonight.
Thank you very much, Roger. Absolutely.
Thank you, everyone.
Shelley, thank you for your donation. And Deep Burrito earlier. Thank you very much. Thank you for all your donations tonight. Much appreciated. Keeps the show on the road. And thank you so much. So we'll just kill this. And there we are. So going to move on now for our last item about time travel this evening. After that, we're going to go for Einstein of the Week and Constellation of the Week to finish the evening. But as I said earlier, there is actually one place in the universe where it's more than possible to travel in time. So what we're going to do is go and have a look at that. And that place, of course, is a black hole. So I'm going to tell you about the relationship between black holes and time travel. So what we know from Einstein's great revelation was that space and time are not separate. They form a single fabric, as Lou was saying earlier, called space-time. Gravity is not a force pulling you down. Gravity is often portrayed as a force because it's easier to imagine it as a force, but it's not. It's the warping of the space-time fabric, and we have to use the word fabric observedly because it's not really a good description of what space-time is, because we tend to portray space-time as a sort of a flat plane, whereas in fact it exists in all dimensions. But you do need to think in 4 dimensions instead of 3. So rather than do that, let's just think of it as a flat plane at the moment. But the point is, as Lou was saying, that the stronger the gravity, the more time slows itself down. Now, Einstein's fundamental insight revolutionized our understanding of the universe and laid the groundwork for understanding black holes. Now, the closer you get to a black hole, the slower time goes. And you may remember we covered this a few weeks ago about black holes. But it leads to all sorts of interesting things happening. A poor astronaut falling into a black hole. Now, for a distant observer, this astronaut falling into the black hole seems to slow down, fade, and freeze at the event horizon. You can never see anything cross the event horizon of a black hole if you're an observer. But for that astronaut, time is completely normal. He crosses the event horizon without noticing anything special at all. But the observer sees the astronaut get slower and slower as he or she approaches the event horizon, and eventually comes to a complete stop, and their image frozen in space. Well, not forever, but a long time, and it gradually dissipates for quantum reasons. So there are 2 realities which are coexisting here, because time itself depends on your point of view. This is the whole paradox about the deeply relative nature of space-time, and it was the genius of Albert Einstein to realize this and to write the theory of relativity, which deals with all of this. Now, Einstein's equations allow another fascinating possibility, and these are called wormholes. Again, a trope of science fiction. You all heard of wormholes, you've seen them portrayed in films. We have to say they're purely theoretical. there's no evidence that they actually exist, no evidence the universe is going to let them exist. But these are theoretical tunnels, if you like, that can connect distant points in space-time, creating shortcuts through the universe. If they could stay open, and that's a pretty big if, one end might age differently from the other end. So if you step through one, you could emerge in a different time as well as a different place. This is the only place we know of in the universe where time travel could be possible. But as they are still purely theoretical, wormholes only exist in maths. They don't seem to exist in reality. They are pure theory. We've never observed them. Keeping them stable and keeping them open long enough for anything to pass through them would require an exotic state of matter with negative energy and therefore negative mass. We don't know what the concept of negative mass actually means. You can do it in the maths by just swapping the plus to the minus sign, and that works fine. But in reality, we have no idea what a material with negative mass would actually mean. That is the only way you could keep a wormhole open. And the math says that quite clearly. So this is why we may never, ever find wormholes and be able to travel through them. Because what in the universe could have negative mass? It sounds crazy, but it does work mathematically. But one thing that is definitely true is a phenomenon called inertial frame dragging. And what happens that any object with mass, if it's rotating, it's dragging space-time around with it. And the more extreme place this happens, the most extreme place this happens is, of course, around a black hole. So the black hole, as it's rotating, its extreme gravity warps space-time so much that it drags it around with it. And you can see in the sort of the little diagram on the left here, the effect that the black hole's intense gravity has on space-time. It's literally twisting it around. And it twists space-time so violently that everything drags around with it. Anything in that space-time gets dragged around as well. This is known as inertial frame dragging. Now, if you could take certain paths through that area shown on the left, you could mathematically and theoretically, I hasten to add, loop back in time, returning to your own past. But these time curves, as they're called, are fascinating. Yeah, they're fascinating, but they're unstable, and nature may forbid them through quantum effects. We don't know. But again, mathematically, theoretically, you could take a path through the area that is being frame dragged by the black hole and return to your own past. But it shows how reality is getting close, as we understand it, to George Herbert Wells' dream of an actual time machine. But this is the only place we know of where it might be possible. So we're back to Doctor Who again, of course. In fiction, I won't go through this too much because Dazzle's already covered some of this. Time travel means changing the past or visiting the future. In physics, black holes show us that time itself can stretch, slow, or even fracture. The effects are real, but the control is limited. And the two ideas meet at the edge of a black hole where imagination and relativity overlap in fascinating ways. So we can think of a black hole as the universe's time machine. We could have infinite time dilation at the black hole. At the event horizon, time dilation approaches infinity relative to distant observers, but you could only go in one direction, forward into the future. When you fall into a black hole, your future is at the singularity. You can only travel into the future via a black hole, although these closed time loops around the event horizon with frame dragging might exist, but we know definitely that that once you fall into a black hole, your destiny is to go straight to the singularity. And if you remember a few weeks ago, we were saying that time and space actually swap places inside the black hole. And this type of time travel is permitted by the laws of nature. Black holes remain the closest thing we have to a real time machine, and it's a testament to the strange and wonderful nature of our universe. So there you have black holes and time travel. the only places in the universe where we're likely to find it at all possible to do any sort of time travel. So
Yeah.
there we are. Okay,
Yeah.
well, as time's getting on, we'll just quickly do Constellation of the. I think we'll do Einstein of the week first, and then Constellation of the week, and finish it off like that, if that's all right with you, Roger. So let me just set this up. So we're going to go to Einstein of the week now. Just give me 1 second to get this set up. And Einstein of the week, of course, is where we take a look through the insanities of social media and what people have been saying on the internet this week about the universe and related things. So just give me 1 second, and I will set this up for you. And here it comes. Just give me 1 second. And here we are. So Einstein of the week for this week, and not many this week, I'm afraid, but we have got a couple. So the first one, this was a lovely new unit of measurement that I came across this week, and this was it. Comet 3i Atlas is losing at least 2 kangaroos worth of dust every second. And bizarre unit of measurement to use there, but you know, I asked the question: is that metric or imperial kangaroos? Of course. So I just thought that was lovely that writers are constantly coming up with new units of measurement to illustrate things. So we now know that dust from a comet is emitted in kangaroos. So I thought that was lovely. Another thing I saw on the internet this week: Mars has water on it because we used to live there, and we destroyed the planet so badly that we had to send an escape pod to Earth with only Adam and Eve in it, and the pod was the asteroid that wiped out the dinosaurs. Yeah. Okay. But it gets weirder. There was no Big Bang. Our galaxy came from our sun shooting out spores into the outer atmosphere. Some spores joined together, then cooling down, forming an asteroid or planet, as we call them. The sun was much larger in its maiden days, but after our billions of years of it spurting out, forming new solids in its outer regions, it has slowly got smaller. Plus, with it getting smaller, it has lost some of its intensity. So, in effect, there's no Big Bang. Well, now you know.
No.
Yeah, I know. And then finally today, back to the comment again, I'm afraid. Could it be that 3i Atlas is returning to Earth on a quantum reversal, since its erratic path may have been the path it left Earth on? If a reversal of a quantum bit is possible in simulation, it very well could be. If humans today can simulate quantum reversal, and an advanced civilization that managed to leave the solar system would have the knowledge, I don't think they would be surprised just visiting an old cemetery. Right. Make of that.
Yeah. It was,
make of that what you will. Anyway,
everybody have been dining on the thesauruses and dictionaries and just putting words together.
Yeah, it's a lovely word salad, without a doubt. Anyway, just thought I'd share those with you viewers. Some madness on the internet this week. So there we are.
Tell you what, we'd be quite ashamed when it all turns out that this is all true.
Yeah, of course.
Yeah.
But to be honest with you, Daz, that ain't going to happen. So there we are. Barry F says a kangaroo is even more than a Rosie O'Donnell. Can't be that much, surely. So there we are. Okay, so lastly, we're going to finish with Constellation of the Week. And apologies we didn't bring this to you last week, but we were running a bit short of time and we didn't want to risk the ire of Derek last week. So I will hand you over to Roger to finish this evening.
I'm going to have to do it in 60 seconds or so here.
Well, I'm sure Derek will give you a pass.
Yeah. Constellation.
He's a nice guy.
In a holding pattern, haven't they? They've been in a holding pattern waiting.
Yeah. So anyway, Constellation of the Week
is Cancer.
Ta-da!
So, ta-da! Yes, one of those other constellations that we won't go into the word, which is mentioned on the slide here.
Exactly.
Okay. So it's one of oh, here we go again. Cancer is the dimmest of the 12 zodiacal constellations, often overlooked, but extraordinarily rich in celestial history and astronomical wonder. So it's between Gemini and Leo, so it forms a distinctive upside down Y shape with just 5 principal stars. So I suppose it would be right side up Y if you were in the southern hemisphere.
Mm-hmm.
It's just our perspective, isn't it?
Yeah. Yeah. True.
Yeah.
True.
So we've got some interesting star clusters which are in this constellation as well. So originally in Greek mythology, it was a valiant crab dispatched by the goddess Hera to distract the mighty Hercules during his legendary battle with the multi-headed Hydra. Through Hercules ultimately crushed the courageous crab beneath his foot, and the goddess Hera honored its sacrifice by immortalizing it amongst the stars. Here we are.
Oh, okay.
Lovely.
But, there's always a doom and gloom, but it got
story,
its
isn't it?
reward in the night sky.
Yeah.
And then we've got the celestial. This powerful myth connects Cancer deeply to enduring themes of struggle, loyalty, and celestial immortality that have resonated through millennia. The story reminds us that even the smallest creatures can earn their place in the eternal heavens through bravery and devotion.
Oh,
So,
lovely.
yeah. I know. So, so we've got it between, so we've got Castor and Pollux of Gemini over there, and then we've got Regulus over to the east of the constellations. So, although it's not particularly a bright constellation, it is visible when the moon isn't quite so favourable. So there we go. So it's an upside down Y rather than a W like Cassiopeia. So we've got the main Y-shaped stars. The brightest stars include Altarf, which is Beta Cancri, Delta Cancri, and Acubans, which I think more people would know of that name. So the stars are usually formed at the bottom of the Y to symbolically mark the crab's powerful claws. So, yes. So, but most of us know Cancer from the M42, which is the beehive cluster, or the Persepe, the manger. Ooh. And this is about 1,000 stars, 577 light years away. So they are roughly gravitationally bound groups of stars. So they can be visible with the naked eye, but it does look better with a pair of binoculars or something a bit more powerful to study it. So it was catalogued back in the 2nd century by Ptolemy. So that was interesting. So he's obviously had some good eyesight.
Yeah.
Before Galileo got his telescope out. And it's one of the brightest star clusters visible from the Earth, and quite favourable with a lot of people to get to know all these different open star clusters as well. And the cluster stars are approximately 750 million years old, so relatively young. So there we are. So we've also got not only the other one, we've got M67, which is another cluster known as the King Cobra cluster. Now, I didn't know that was also called that. Yeah, so that's roughly 3,000 light years distant, and is one of the oldest known open clusters, aged exceeding 4 billion years. So that's also visible with binoculars or a small telescope. So have a look for that one. So the main stars we've got is Beta Cancri, which is Altarf, and is a double star system with a K-type star, and a faint red dwarf. Delta Cancri is located in the center, as known as the heart of the celestial crab. And then the brightest one, Acubans, Alpha Cancri, is a binary. and that is quite interesting to see, as you can see them through the telescope quite nicely.
Yeah, right.
So we've got several stars in Cancer have been confirmed as having exoplanets orbiting them, so that's quite interesting. So we've also got treasure trove of dedicated deep sky objects, and we've also got Mars and Jupiter occasionally pass near Cancer as well, so that can be quite a good photo opportunity with the M44 Persepe as well, so good opportunities there. So best to see it in the northern hemisphere between March and May when it reaches its peak, and that will be around about 9 to 10 o'clock local time in mid-March, so still pretty good for viewing there before the clocks go back, so that's quite good. We won't look at the southern hemisphere because they don't count.
They don't.
Okay. So the Tropic of Cancer earned its name because the sun once appeared within the constellation in the summer solstice about 2,000 years ago. So that's why it was called the Tropic of Cancer. So I assumed that the Tropic of Capricorn would also be the reason why it's at a different point, obviously, but not 2,000 years ago, maybe. I don't know. I haven't done that. But it's always permanent links Cancer to Earth's geography, ancient astronomy, and our understanding of celestial mechanics. And due to the Earth's axial precession, the slow wobble in the planet's rotation, the sun now appears in Gemini during the summer solstice. So no longer in Cancer. So that's probably why it was 2,000 years ago.
Yeah.
That makes sense.
Yep.
So the zodiacal significance is symbolizing emotion, home, nurturing, and protective instinct. The lunar rulership in astrology. Should I be reading this? Is ruled by the moon, associated with the element of water, obviously because crabs like to be in water, don't they?
I don't know.
Symbolic meaning. So we've got its protective shell and tenuous loyal nature in both mythology and modern interpretation. So
right.
There we go. There we are. So
Thank you very much.
Hopefully we've had a few tidbits of information that we didn't have before we started.
Yeah, definitely. So, there we are. So that's the Constellation of the Week for this week. And that, viewers, brings us to the end of tonight's show. Thank you so much for watching tonight. We hope you've enjoyed it. Thank you so much for your donations this evening. Much appreciated. As I always say, you're probably fed up with me saying it, but just to reiterate that all the money donated to us goes towards keeping Space Oddities going. So thank you so much for your support. If you like what we do, then your support is appreciated. And we will be back, of course, same time next week. And not quite sure what we're doing yet. We're just organizing that at the moment. So keep an eye on the channel, and also keep an eye on the website, because we do post what's coming up on the channel on the website as well. So there we are. So it's been a great evening. Thank you all so much for being here. So from Daz, from myself, from Michael in the chat, who's unwell and hasn't been able to join us in the studio tonight. I hope you're feeling better soon, Michael. And from in absentia, thank you from Lou as well. Lou had to go off to teach earlier, so there we are. So we will see you next week at the same time here on Space Oddities, 8 p.m. UK on the channel, as always. And thanks again for being here. And we love you loads, and have a fantastic week. So from all of us, goodbye.